Welcome to our channel where we explore the fascinating world of STEM. Discover remarkable scientific discoveries and innovations that shaped our world and explore the stories of brilliant minds who made them possible. Our goal is to inspire a love of learning and passion for STEM while broadening your horizons and deepening your understanding of the world. Come with us and explore the wonders of science, technology, engineering, and mathematics. The special theory of relativity is a fundamental theory in modern physics that explains the behavior of objects moving at high speeds. It was developed by Albert Einstein in 1905 and is based on two postulates. The laws of physics are the same for all observers in uniform motion relative to one another, and the speed of light in a vacuum is constant, independent of the motion of the observer or the source. In this thesis, we will provide an overview and analysis of the special theory of relativity, its key concepts, and its implications. Historical context and development. The special theory of relativity is based on two postulates. The laws of physics are the same for all observers in uniform motion relative to one another, and the speed of light in a vacuum is constant, independent of the motion of the observer or the source. The first postulate, known as the principle of relativity, states that the laws of physics are the same for all observers who are in uniform motion relative to one another. This means that the fundamental laws of physics, such as the laws of motion, are the same for all observers regardless of their relative motion. For example, a person in a moving car would observe the same physical laws as a person standing still on the ground. The second postulate, known as the speed of light postulate, states that the speed of light in a vacuum is constant, independent of the motion of the observer or the source. This means that the speed of light is the same for all observers, regardless of their relative motion. Even if the observer or source is moving at a very high speed, the speed of light remains constant. These postulates were necessary to develop the special theory of relativity because they contradicted the classical view of motion. According to classical physics, time and space were absolute and independent of each other. This view was based on the assumption that the laws of physics were the same for all observers, regardless of their relative motion. However, this assumption was challenged by the results of the Michelson–Morley experiment, which showed that the speed of light was constant, independent of the motion of the observer or the source. Einstein's postulates led to a new understanding of space and time, in which they are not absolute, but are relative to the observer's motion. This new understanding is based on the concept of space-time, which combines space and time into a four-dimensional continuum. The speed of light is the same for all observers in space-time, and this leads to time dilation, length contraction, and other relativistic effects that are observed at high speeds. The postulates of the special theory of relativity differ from the classical view of motion in that they challenge the assumption of absolute space and time. According to the special theory of relativity, space and time are relative to the observer's motion, and this leads to the relativistic effects that are observed at high speeds. This new understanding of space and time has led to a revolution in physics and has led to the development of new technologies, such as GPS, that rely on the principles of relativity. Lorentz transformations and time dilation. The mathematical concepts and calculations of the special theory of relativity are based on the Lorentz transformations, which describe the way in which time and space are affected by relative motion. The Lorentz transformations are a set of equations that relate the coordinates of an event in one reference frame to the coordinates of the same event in another reference frame that is moving at a constant velocity relative to the first reference frame. The Lorentz transformations are based on the assumption that the speed of light is constant, independent of the motion of the observer or the source. This assumption leads to the phenomena of time dilation, length contraction, and relativistic mass, which are observed at high speeds. Time dilation is the phenomenon in which time appears to slow down for objects that are moving at high speeds relative to an observer. This means that a clock that is moving at a high speed relative to an observer will appear to tick slower than a clock that is at rest relative to the observer. The amount of time dilation depends on the velocity of the moving clock relative to the observer and is given by the formula T equals T sqrt 1 versus squared c squared, where T is the time interval between two events as measured by an observer at rest relative to the events. T is the time interval between the same two events as measured by an observer in motion relative to the events, v is the relative velocity between the two observers, and c is the speed of light. The Lorentz transformations also predict length contraction, which is the phenomenon in which the length of an object appears to be shorter when it is moving at high speeds relative to an observer. This means that an object that is moving at a high speed relative to an observer will appear to be shorter in the direction of its motion than the same object at rest relative to the observer. In addition, the Lorentz transformations predict relativistic mass, which is the increase in mass of an object as it approaches the speed of light. This means that an object that is moving at a high speed relative to an observer will appear to have a larger mass than the same object at rest relative to the observer. Length contraction and relativistic energy. Length contraction is a phenomenon predicted by the special theory of relativity, which states that when an object moves at a high speed relative to an observer, its length in the direction of motion appears to contract. This effect occurs because the speed of light is constant and does not depend on the motion of the observer or the source. As a result, time and distance must be relative to the observer, and the measurements of these quantities must be corrected when the observer is in motion. Length contraction is given by the formula L equals L, sqrt, 1 versus squared, c squared. Where L is the length of the object in its rest frame, L is the length of the object as measured by an observer moving at a velocity v relative to the object, and c is the speed of light. Relativistic energy is the energy that an object has due to its motion, and it is given by the formula E equals mc squared, sqrt, 1 versus squared, c squared. Where m is the mass of the object, c is the speed of light, and v is the velocity of the object. This equation shows that an object's energy is proportional to its mass and the square of the speed of light. As an object's velocity approaches the speed of light, its energy and mass both increase without limit. The relationship between mass, energy, and velocity led to the famous equation E equals mc squared, which states that mass and energy are two forms of the same thing and are interchangeable. This equation shows that a small amount of mass can be converted into a large amount of energy and vice versa. The equation E equals mc squared has many practical applications, including in nuclear energy and nuclear weapons. It also has important implications for the structure and evolution of the universe, as it shows that energy and matter are intimately connected and that the total energy of the universe is conserved. Implications and applications of the special theory of relativity. The special theory of relativity has had a profound impact on physics and our understanding of the universe. It has led to a significant shift in our understanding of space, time, and the behavior of objects at high speeds. One of the most important implications of the theory is that the laws of physics are the same for all observers, regardless of their relative motion. This principle, known as the principle of relativity, has been shown to hold true in numerous experiments and observations. The theory has also had significant practical applications in areas such as GPS technology and particle accelerators. The accuracy of GPS technology depends on the precise measurement of time, and the special theory of relativity predicts that time passes more slowly in a strong gravitational field or for objects that are moving at high speeds. Without taking this effect into account, GPS devices would be inaccurate by several meters. Therefore, the theory's prediction of time dilation has been crucial for the development of accurate GPS technology. The development of particle accelerators, which are used to study the behavior of subatomic particles, has also been greatly influenced by the special theory of relativity. The theory predicts that as the velocity of a particle approaches the speed of light, its mass and energy increase without limit. Therefore, particle accelerators must take this effect into account to ensure that the particles they accelerate do not become too massive to be accelerated further. The theory has also provided a framework for the study of high-energy particle physics, which has led to numerous discoveries about the behavior of matter and energy at the smallest scales. Another practical application of the special theory of relativity is in the development of nuclear energy. The equation E equals mc squared shows that a small amount of mass can be converted into a large amount of energy, which is the principle behind nuclear energy. The theory has also been used in the development of nuclear weapons, which rely on the conversion of mass into energy. Criticisms and limitations. Despite the significant impact of the special theory of relativity on physics, there have been criticisms and limitations associated with the theory. One of the key debates surrounding the theory is the question of whether or not it is possible to travel faster than the speed of light. The theory states that nothing can travel faster than the speed of light, and this principle has been supported by numerous experiments and observations. However, some physicists have proposed the existence of hypothetical particles known as tachyons, which are thought to travel faster than the speed of light. The existence of tachyons is still a subject of debate and has not been confirmed by any experimental evidence. Another criticism of the theory is that it assumes that the laws of physics are the same for all observers, regardless of their relative motion. This principle, known as the principle of relativity, has been shown to hold true in numerous experiments and observations. However, some physicists have argued that there may be exceptions to this principle, particularly at very small scales or in the presence of strong gravitational fields. Another limitation of the theory is that it only applies to objects that are moving in a straight line at a constant velocity. Objects that are accelerating or moving in curved paths are not fully described by the special theory of relativity and require the use of the more general theory of relativity. There have also been debates surrounding the implications of the theory for our understanding of space and time. Some physicists have argued that the theory suggests that time and space are not absolute but are relative to the observer's frame of reference. This idea has been a subject of philosophical debate and has led to discussions about the nature of reality and the limits of human perception. In conclusion, while the special theory of relativity has had a significant impact on physics and our understanding of the universe, there have been criticisms and limitations associated with the theory. The question of whether or not it is possible to travel faster than the speed of light remains a subject of debate, and there may be exceptions to the principle of relativity in certain situations. The theory also has limitations in its applicability to objects that are accelerating or moving in curved paths. Despite these limitations, the special theory of relativity has provided a powerful framework for understanding the behavior of matter and energy at high speeds and has led to numerous practical applications while remaining a key component of modern physics and continues to inspire new research and discoveries. Thank you for joining us on this journey of discovery and exploration. We hope you've enjoyed learning about the wonders of science and the incredible breakthroughs that are shaping our world. From uncovering the mysteries of the universe to tackling some of the most pressing challenges facing humanity, science truly has the power to transform our lives and our world. We invite you to continue exploring the amazing world of science, and to join us in our mission to promote scientific understanding and knowledge. Stay curious, keep learning, and always keep asking questions. Who knows what incredible discoveries lie ahead? Thank you for being a part of our community, and we look forward to continuing this journey together.